All right, physics students, today we're going to talk about net forces, and the word net force basically means the sum of all forces on an object. Okay, and it's what you have left over. So we can sometimes represent that with the Greek letter sigma, F. That means the sum of all the forces. And it's what you, like I said, what you have when you're all done. Now, according to Newton's second law, the sum of all the forces is equal to the mass of an object times its acceleration. And we can actually solve this in multiple directions since we're going to be working in more than one direction. So we can have the sum of the forces in the x direction equals the mass times the acceleration in the x direction, and we can have the sum of the forces in the y direction equal to the mass times the acceleration in the y direction. And so I'm going to take you through a few examples now. I am going to show you how to make some free body diagrams here, and from those diagrams create some physics equations. So the first picture here, I have an object that is at rest and it's just sitting on a surface like a tabletop. And so we want to talk about what forces exist here. Well, I know that this object is being pulled down by the force of gravity, and so we call that F sub g. I also know that it's not falling through the tabletop, so the tabletop must be pushing up on it, and we call that upward push the normal force. Now, if I'm going to do this as a free body diagram, I just draw it as a dot, and then I take those two forces and I attach them to the dot. Now notice I made those two arrows the same size, and why did I do that? Well, I know the object is at rest, and if the object's at rest, it means that the acceleration here is equal to 0. And if the acceleration is 0, then I know that the net force, this is the Greek letter sigma, it means the sum of all my forces must equal 0 as well. So I would show that in the x direction, there are no forces here. So I'm going to just say sum of the forces in the x direction is 0. In the y direction, I know that sum is 0, but I want to expand it to show that it's made up of two other forces, F sub n, and I'm going to subtract F sub g. Now, why do I subtract F sub g? Down is typically the direction that we call negative. Okay, I could go F sub g minus F sub n if I wanted to say up was negative, but we don't typically do that. We know that this is equal to the mass of the object times its acceleration in the y direction, but we know that there is no acceleration. It's not moving. So this truly equals 0. All right, and you could just cross this out and put 0 if you wanted. All right, so then let's take a look at the next example. Now we have an object that's moving, all right, but it's moving at a constant velocity and there is friction present. So this is a little bit more interesting. We still have the same two forces that we had before. We have F sub n, the normal force, and we have gravity pulling it down. Gravity never goes away. And we know that friction is present, and friction is going to always oppose your motion, or at least the direction that an object would want to go. And because it's moving, we know that it's kinetic friction. Well, if the object is moving at a constant velocity, that's a key phrase for us to know that the acceleration of this object is 0. And if the acceleration is 0, that must mean that the sum of all the forces is also 0. So there must be something balancing out this kinetic friction. And that's going to be a force that we call the applied force. So you might be pushing on it, you might be pulling on it, something like that. So now I'm going to sum up my forces in both the x and the y direction. So in the x direction, I have these two forces, F applied and Fk. Now typically we say that the right is our positive direction and the left is our negative. Again, kind of look at the problem that you're dealing with and then decide which one you want to be positive or negative. It doesn't really matter as long as you stay consistent throughout the problem. So I'm going to say F applied is positive, and so I'll say F applied minus F sub K, and I usually have K be my negative one just because friction never helps like your motion. It always goes against your motion, so that means to me that it would be negative. And we know that this equals 0. In the y direction, we have the same thing we had over here. F sub n minus F sub g equals 0. All right, there is no acceleration, therefore there are no forces. Again, I could, if I wanted to, set these equal to, set F sub x equal to MAY, knowing, or I'm sorry, MAX, knowing that this is going to be 0, right? But what I'm trying to do is I'm trying to include what forces are present here. And this can be helpful because if I know the applied force, maybe I want to know how much friction there is. And if I know they're equal, and I know one, I can know the other. All right, let's move on. Now we have an object that's speeding up with friction present. So how is this going to be different than an object moving at a constant velocity? Well, in this case, acceleration is not 0. Okay, so when I sum up my let me look at my forces here first. I've got F sub g, F sub n. I've got an applied force, and that applied force is going to have to actually be bigger than my frictional force. Let me pull this down here as a free body diagram. F sub n, F sub g, F applied, and Fk. So how do I know to make k smaller? Well, I know that one of these forces has to win. I know that the sum of the forces can't be 0 because the acceleration isn't 0. And I know that actually it's not just acceleration, it's acceleration in the x direction. In the y direction, it's not sinking into the table, it's not getting pushed off the table, so there is no acceleration in the y direction. So when I sum up my forces, I go F sub x equals F applied minus F sub k, just like I did up here. But there, it was 0 because it wasn't accelerating. Now it is accelerating. And so I'm going to have to leave it as MAX. And I don't know what the answer is here, but this is the correct equation to describe that motion. In the y direction, it's the same as it was before. F sub n minus F sub g. And that equals MAY, but like I said, the acceleration in this situation is only in the x direction. If it was accelerating upward, it would have to be getting popped off the table somehow or sinking into the ground. That doesn't happen. So again, this is just going to end up being 0. And you're going to find out that that works out that way almost every single time. All right, so now let's take a look at a coasting object. All right, so here I have a normal force. Here I have gravity. Here I have no applied force this time because it's just coasting. So it's, somebody gave it a push at some point and now it's not doing that anymore. So there is no applied force this time. Let me pull that out into a free body diagram. F sub n, F sub g, F sub k. So this one you can tell is unbalanced. So let's go ahead and, what do you think is going to happen here? If an object is coasting on the ground and there's friction, it's going to eventually come to a stop. So I go, the sum of the forces in the x direction is, well, all I have is friction. So that's going to be F sub k equals MAX. Now this is going to end up, if going to the right is my positive direction, F sub k needs to be negative. And that's going to give me ultimately a negative acceleration, which makes sense because the acceleration for a coasting object would be negative. It'd be going against the motion. In the y direction, guess what? It's going to be exactly the same as it was over here. There is no change in the motion moving up or down. So that's going to be F sub n minus F sub g, once again, equals 0. All right. Then the last two that we have here we have an object in true free fall. And remember I said that really never happens here on Earth because we always live in air. If you could go to the moon, you could have an object in true free fall. But what what's occurring here? Well, when an object is falling, why is it falling? It's falling because of gravity. Now you might say, well, there's a normal force as well, but there is no normal force in this situation because there is no contact. Normal forces only happen when there are two surfaces that make contact. So there is no normal force. All right, so what does that mean? There's no other forces. Nothing's pushing it to the left or right. There's nothing pushing up on it. And that means that the sum of our forces in the x direction is 0 because there are no forces in the x direction. In the y direction, let me draw that free body diagram. That's it. It's just F sub g equals MAY. And that, guess what? That AY is going to be negative 9.8. Let's make this a negative sign just because we know it's moving down. Last example, let's say it's falling. Now it isn't true free fall, it's falling, but there is air resistance. Well, I still have gravity. Gravity never shuts off, but now I have the force of air resistance pushing up on the object. And it can be smaller or it can be larger. If it reaches terminal velocity, then we know that it's going to be equal. But I still have no sideways forces, so I'm still in the same situation as I was before. Here's the force of air resistance. Here's the force of gravity. And when I sum up my forces in the y direction, it's going to be now F air resistance minus Fg equals MAY. And again, if they're equal, it's going to be 0. That would be terminal velocity, but again, no forces in the x direction. All right, that is it. Peace.